Hey there. In this video, we're going to learn about Frobenius series solutions. We are going to learn the method of Frobenius to find series solutions to differential equations near singular points. First, we need to talk about how we classify singular points. We've talked about ordinary points. Now, a singular point is where if I have a differential equation, like this one, for example, where there's polynomial coefficients and the coefficients are a2, a1, and a0, and if none of them have common factors, then the singular points are going to be where that leading coefficient, a2, is equal to 0. If I put this differential equation into standard form, I can identify the p of x and the q of x that are multiplying by a prime and or y prime and y. And I get this standard form by dividing the entire differential equation by a2, that leading coefficient. So let's say I identify some singular point. This is where a2 at that point is equal to 0. If I take and multiply p of x times x minus x naught, so x minus my singular point, and then I multiply q of x times x minus x naught squared, I get these two functions. We'll call them lowercase p and q. And if they're analytic at x naught, then I can say that this is a regular singular point. And regular singular points are basically, they're well-behaved. I have more predictable solutions to differential equations. So these are the ones we're going to focus on solving in this video. And if they're not regular singular points, then they're irregular singular points, and we're not going to deal with those today. Okay, so let's just get an example to get an idea of classifying regular versus irregular singular points. So here I have a second order homogeneous differential equation, x minus 1 squared y double prime plus x minus 1 times y prime minus y equals 0. So it's not in standard form, but I can identify my singular points by taking a sub 2, which is the leading coefficient, multiplying by my second derivative, and setting that equal to 0. So here that's going to be x minus 1 squared equals 0. And if I solve this, I'd square root both sides and add the 1 over, and I get a singular point at x naught equals 1. So I want to see now, is this a regular singular point or an irregular singular point? So putting the differential equation into standard form, I divide by x minus 1 squared, and I get p of x is 1 over x minus 1. Because one of the x minus 1's canceled there. And then I get a q of x of negative 1 over x minus 1 squared. So I want to take each of these functions, these coefficients, and multiply them by a power of x minus 1, since my singular point was 1. So for lowercase p of x, this is going to be x minus 1 times uppercase p of x, which is 1 over x minus 1. And that just simplifies to 1. And that is going to be analytic at p of x. I could write that as a power series. For q of x, that's going to be x minus 1 squared now times uppercase q of x. So that's times negative 1 over x minus 1 squared. So that simplifies to negative 1. It is also analytic at x naught equals 1, which means that this is a regular singular point. If I had gotten something like 1 over x minus 1, for instance, for either p of x or q of x, then it wouldn't be analytic there. I have that discontinuity in the denominator, and that would have been an irregular point. Okay, so now let's see. Once I've figured out that I'm dealing with a regular singular point, this is when I can use Frobenius's method. And Frobenius's theorem tells us that if I have a regular singular point, x naught, for the second order differential equation, then there exists at least one solution of this form. So there's one power series solution that's the sum from n equals 0 to infinity of Cn, so those are my unknown coefficients, times x minus x naught to the n plus r. So it's very similar to ordinary points. The big difference is that plus r. And also the fact that this theorem is only guaranteeing me that I can find one solution of this form. There's no guarantee that there's going to be two solutions like we had with ordinary points. So we're going to follow a very similar method to what we used for finding solutions around ordinary points, but we're going to have the added job of identifying this value r, which could have more than one value to it, but we're going to be looking for values of r in addition to the coefficients here. So this method is called, before I move to that, so this series is convergent on some interval between 0 and r, and there is no guarantee that I'm going to get two solutions from this, of this type. Okay, so with method of Frobenius, I'm going to add that plus r to my exponent to make that little adjustment since I'm dealing with a regular singular point instead of an ordinary point. We call that r the indicial root. Doesn't make sense why we call it a root yet, but when we see how we're going to come up with that value, that's where it comes in. And so the method is pretty similar to before with a little some extra steps. So first I'm going to identify that I'm dealing with a regular singular point before I go through this process. And then I'm going to assume I have that power series solution that we have here with the added r in there. And then just like we did with ordinary points, I'm going to line my powers of x minus x naught so they're all the same power. This time it's going to be something like k plus r instead of just to the kth power like we did before. And then I'm going to re-index all my sums so that they start at the same value. Usually that means stripping some values out of some of the series that start earlier. And then I'm going to condense that sum down to a single sum. The coefficients that I strip out are going to give me an indicial equation that I'm going to solve to get that r, the indicial root. And then I'll form my recurrence relation to find the first few terms in the sum and get my final solution. Okay, so let's do an example using this method. So I've got 4xy double prime minus y prime plus 4y equals 0. Looking at that 4x in the leading term, I'm thinking 0 is going to be my singular point because if I divide this all by 4x, I'm going to get an x in the denominator. Okay, so doing that, I get y double prime minus 1 over 4x y prime plus 1 over x y equals 0. And so I do have a 0. 0 is not part of the domain of those two functions, p of x and q of x. So it is a singular point. It's not analytic there. And so if I find little p of x, that's going to be x times negative 1 over 4x, which simplifies to negative 1/4. That's going to be analytic at 0. And little q of x is x squared times 1 over x, which simplifies to just x, which is also analytic at x equals 0. Okay, so p of x and q of x are analytic at our singular point, which means that 0 is a regular singular point. So we're all clear to go forward with the method of Frobenius, and we should find at least one solution, maybe two, from solving using this method. Okay, so this means that my proposed solution is this sum from 0 to infinity of cn x to the n plus r. So I just plugged in 0 for my x naught, and I get this. It's a second order differential equation, so I need the first and second derivatives of this to plug into the differential equation. So just using the power rule, I'm going to get a derivative from 0 to infinity. And note, I'm not starting at a later index this time like I did with ordinary points because of the r. Okay, there's an unknown r in there. I don't necessarily lose the first term. So all of our derivatives are going to be starting at n equals 0. So the derivative of that nth term is going to be cn times the exponent n plus r times x to the n plus r minus 1 now. Doing power rule one more time to get the second derivative. I'm still starting at 0 for my sum. I'm going to infinity. And now it's going to be cn times n plus r times n plus r minus 1 times x to the n plus r minus 2. Okay, so I've got y and its first two derivatives, and I can plug everything now into this differential equation. Okay, so plugging it all in, I get that second derivative times 4x. And so it was an x to the n plus r minus 2. When I multiply it by x, that becomes an n plus r minus 1. And then the other two are just as is. I just added a 4 to times the y and a negative out in front of the y prime. And now we've got everything plugged into our homogeneous differential equation. Okay, so the first thing I want to do is I want to get these exponents on my x's to match. And I'm not trying to get rid of the r, I'm trying to find r ultimately. So I'm going to make all of these have an exponent of k to the r, or k plus r, when I'm all done. So the first one, I want to use the substitution k equals n minus 1. So that'll get rid of everything around the r. And the same thing for the second one, since they have matching exponents. The third one has the exponent I want already, so I'm just going to swap out the n for the k, so all my variables match. Okay, so going to the first one, I'm going to replace the starting value was 0, so if n's 0, then that means 0 minus 1 gives me a starting value of negative 1 this time, which feels a little weird. We normally don't have series that start at negative values, but it's absolutely possible for that to happen. So we end up with a series at k equals negative 1 to infinity. And everywhere there's an n, I'm going to swap it out for k plus 1, since that's what n would be equal to if I solve that little equation, k equals n minus 1. So I end up with an nth term, or a kth term now, of 4ck plus 1 times k plus r plus 1 times k plus r times x to the k plus r. Okay, so going to the next one, same thing. This one's also going to start at negative 1 now. And my kth term is going to be ck plus 1 times k plus r plus 1 times x to the k plus r. And the last one, I'm just swapping out n's for k's, so that one doesn't really change. It still starts at 0, and I have 4ck times x to the k plus r. And all of this adds up to 0. Okay, so things are looking good. My x's have the same power on them, and now I just need to get all my sums to start at the same value. So the latest one is the k equals 0 in the third sum. So I need the other two to start at that same value. So I'm going to take out the k equals negative 1 term from those first two sums. Okay, so in the first sum, if I plug in negative 1, I'm going to get 4 c0 times r minus 1, all times x to the r minus 1. And then if I go to the second sum and pull its first term out, where k equals negative 1, I'll get c sub 0, or minus c0, times r times x to the r minus 1. And now all three of my sums are starting at 0, so I can combine them into a single sum and factor out the x to the k plus r. Okay, so there's some cleanup I can do before I start trying to solve for r and find my recursive relation. Those first two, they both have a c naught in them and an x to the r minus 1, so I can factor that out, clean it up a little bit. And inside of my sum, I have two ck plus 1 terms, so I can factor the ck plus 1 out. And they also have a k plus r plus 1 in common, so I can factor that out as well to clean up these the sum inside of here. Okay, so if I do all that, I end up with a leading term out in front of the sum of c naught x to the r minus 1 times 4r times r minus 1 minus r. And then inside of the sum, I have ck plus 1 times r plus k plus r plus 1 times 4k plus 4r minus 1. And then I still have that 4ck following it. And all of that is multiplied by x to the k plus r. Okay, so it's as cleaned up as it's going to get. And now it's time to find my r values and then use that to find the first few terms of my solution. Okay, so the coefficient that is multiplying by c naught x to the r minus 1 is going to be the equation I solve for r. Now, one of the bedrocks of the method of Frobenius is that we're always going to assume that c naught is not 0. Okay. Normally we say that, some of them might be arbitrary and unknown, and then the rest of the c's have to equal 0. Here, we're always going to start with that first constant is not equal to 0. And so that means that in order for this term outside of the sum to be equal to 0, which it needs to be since the whole series, or the whole left side is equal to 0, then that means that the 4r times r minus 1 minus r has to be equal to 0. So this is what we call the indicial equation. And I can clean this up a little bit. If I distribute the 4r and combine like terms, I'm going to get a 4r squared minus 4r minus r. So that's 4r squared minus 5r equals 0. And now that those terms have been combined, I can factor out an r. So I get r times 4r minus 5 equals 0. And that gives me two indicial roots of 0 and 5/4 by just setting each of those factors equal to 0. So I got two roots for this equation, which means I'm going to get two solutions. Okay, so now that I found my indicial roots, I'm going to go to the sum and find my recursive relation. And then I'll plug in my values for r to that function so I can start getting those two solutions. So first I take that the constants inside of the sum, set them equal to 0. And then I'm going to solve for the higher or the later term in the sum. So ck plus 1 comes after ck. So I'm going to solve this equation for ck plus 1. So that means subtracting 4ck to the right and then dividing by everything, multiplying by that ck plus 1. And it gives me this recursive relation. So ck plus 1 is equal to negative 4ck over k plus r plus 1 times 4k plus 4r minus 1. And this starts at k equals 0 and goes from there because that is where the sum started at k equals 0. Okay, so now I can take my indicial roots. I'll start with the first one, r equals 0. I'm going to plug it in for r and clean up this recursive relation. And I get ck plus 1 equals negative 4ck times k plus 1 times 4k minus 1. And I can use this to find the first few terms of my power series solution. So I'm just going to find the first three terms and plug in 0, 1, and 2 to get my first three terms of the solution. So if I plug in k equals 0 to this formula, I get c1 equals 4c naught. Again, we don't know what c naught is, but we know it's not 0. So we're going to keep it and move to the next one. If k equals 1, then c2 is going to equal negative 2/3 c1. And since I just found that c1 is equal to 4c naught, I can plug that in for c1 and I get negative 8/3 c naught for my second term. And then for the third term, c3 is going to equal negative 4 over 21 times c2. And c2 is negative 8/3 c naught. So I will multiply that by the negative 4 over 21 to get 32 over 63 c naught. So all of my terms end up being in terms of c naught, which is very good for that final solution. Putting together the final solution from this particular indicial root is going to be y1 equals c naught times x to the r. So I'm factoring that part out. And then all times my my power series. So 1 plus c1x plus c2x squared and so on. So using the coefficients I just found, my first solution, y1 equals c naught times 1 plus 4x minus 8/3 x squared plus 32 over 63 x cubed and so on. Okay, so to find the second solution, now I'm just going to switch r to 5/4 and repeat those last few steps. So if I plug in the 5/4, I end up with ck plus 1 equals negative 4ck over k plus 1/4 times 4k plus 4. Now, you can just use it in this form. For me, I like to clean it up a little bit. It's kind of a pain to be plugging this in with that 1/4 in there. And it so happens that I can factor a 4 out of the 4k plus 4 and then distribute it to the k plus 1/4 to eliminate that, that fraction. So if I do that, I end up with negative 4ck times 4 or divided by 4k plus 1 times k plus 1. So just a little nicer. It's not a necessary step, but it does make life easier when you start plugging values into this. Okay, just like before, I'll start with k equals 0. And plugging in 0 to this recursive relation, I get c1 equals negative 4c naught. Plugging in k equals 1, I get c2 equals negative 2/5 c1. Multiplying that by what we found for c1 above, I get 8/5 c naught. And I'll go one more term with k equals 2. I get C3 equals negative 4 over 27 C2. And then plugging in the 8/5 C naught for C2, I get 32 over 135 C naught. Okay, and just like before, to get my solution for y2, it's going to be C naught times x to the r times the power series 1 plus C1x plus C2x squared, and so on. Now, the previous one, r was 0, so the x to the r term just turned into a 1. Here, r is not 0, so I am going to have a power of x out front. So y2 is C naught x to the 5/4 times 1 minus 4x plus 8/5 x squared plus 32 over 135 x cubed, and so on. So I did luck out, and I got two solutions from this particular differential equation using this method. If I wanted to write the general solution, I would write these two solutions as a linear combination. And that is how you use the method of Frobenius. Now, just one note, if for some reason you just wanted to find the indicial roots, you can find the series expansion of little p of x and q of x, which would look like this. And I can derive the indicial root or the indicial equation without going through all of the steps we just did of plugging in the proposed solution and simplifying it. And that general formula for the indicial equation, and this is just for second order differential equations, but it would be r times r minus 1 plus a naught r plus b naught equals 0.